Welcome to the New Quantum Era podcast. In this episode, I'll be joined by Dr. Eli Levenson-Falk, Associate Professor of Physics, Astronomy, and Electrical and Computer Engineering at the University of Southern California. Eli got his PhD at UC Berkeley while working with Professor Irfan Siddiqui and now leads an experimental research group at USC working primarily with superconducting devices and their applications in quantum information science. Our conversation today is going to be primarily about the work that Eli's group did recently that was published as a paper titled Beating the Ramsey Limit on Sensing with Deterministic Qubit Control, which appeared in Nature Communications in April 2025. The paper describes a novel protocol for making measurements on quantum devices that are more sensitive than the Ramsey measurement limit, and you'll hear how the coherence stabilized technique may be used for more robust computation on superconducting devices with potential sensing applications on superconducting devices and other types of quantum devices as well. We'll dig into Eli's journey from playground physics to cutting-edge quantum experiments, unpack the fundamental challenges of decoherence, and discuss the implications for both quantum computing and sensing. Eli will be sharing the story behind his experimental work and talking about the collaboration with the theorist Daniel Ladar, who we've had previously on the podcast, and how subtle improvements in control can lead to significant advances in calibration, measurement speed, and sensitivity. I'm personally always really fascinated by the nuts and bolts of quantum hardware design and experimentation, and I found my conversation with Eli really compelling. Let's get started with Dr. Eli Levenson-Falk. So I wanted to ask you first just to briefly introduce yourself before we get into the conversation.
Yeah, I'm Eli Levenson-Falk. I'm an associate professor of physics and astronomy and of electrical and computer engineering at the University of Southern California. And I run an experimental research group using superconducting circuits for quantum information science.
That's awesome. That's such an interesting mix of different specialty areas. How did you sort of arrive at that combination of astronomy and electrical engineering? And
well, so the department is the Department of Physics and Astronomy.
Okay.
So if you're one, you're automatically the other.
I see.
And
Interesting.
My own astronomy knowledge is not great,
Gotcha.
Which is really too bad because all anyone wants to hear about is space. But we're trying to convince them to be excited about quantum too.
Yeah. Yeah. Well, and, space works on quantum. So, so I wanted to talk to you because you did some recent work that was published in Nature that I thought was super interesting, developing a new protocol for quantum sensing that improves the performance of superconducting devices in that sensing kind of application. Is that right?
Yeah, I mean, it's really more of a protocol, and so it will apply to other types of devices too. It's not just superconducting.
Oh, interesting.
I mean, we demonstrated it on a superconducting device because that's what I work with.
Right.
But it's really the way that we did the control that is the important thing, and that's a very general thing that would apply to a lot of technologies.
Interesting. So, I mean, it's not specific to sort of microwave pulse interactions with a superconducting device?
No, it really will work on any technology where you can do what we'll call a continuous control, where you can just sort of be slowly, pushing it towards something continuously over time, where you don't have to just only do pulses.
I see.
And that's most technologies. There are a few where you can really only do things in sort of discrete pulses. But for most of them, you can do something continuous.
Interesting. So in this case, there is, I mean, microwave pulses are sort of the main way that you interact with, calibrate, do gate operations with a superconducting qubit. What would be the way that you would apply continuous control?
So it's just very, very long, very, very slow microwave pulses, basically.
Oh, I see.
And
okay.
We're just sort of varying the strength as it goes. So you can think of it as just like a continuous microwave drive.
Right. Okay.
And I mean, one way to look at it is the whole point of what we're doing is to learn the difference in energy of two quantum states. That's the thing we're really trying to sense. In order to get a system to switch between those states, you drive it at a frequency that corresponds to that energy difference.
Right.
The stronger your drive is, the faster it will transition. And so if you can vary the drive strength, then you can sort of do this continuous control. And that's what we do.
I see. Interesting. So then I remember, there's a couple of instances. So you can think of the microwave pulses as being like, the almost the content on the carrier signal. So this sounds more like almost like the carrier signal itself. Is that?
I would say it's the amplitude of the carrier signal.
Okay.
Yeah. So there's a carrier signal which is what controls the fact that you're actually driving this transition at all. And then there's the amplitude of it, which sort of controls how fast you're doing it.
How fast? Okay, that makes sense. And so, what was the sort of the secret sauce that led to this new protocol? What does it distill to?
Yeah, so it actually started as just trying to demonstrate a toy model that we didn't really think was going to have anything to do with sensing. So the idea is that when you have a quantum system, you can put it in a superposition of more than one state. Typically we'll deal with the simplest possible thing, which means there's only two states, and you put it in a superposition of those two states. And what happens is, because of interactions with the environment that we don't control and that are kind of noisy and random, this state gets scrambled. And so then if you do the experiment again, you get a different result.
Right.
And not in the sort of like quantum probability way, but in the sort of just like noise scrambled things and mess things up. And we call that decoherence. Basically the degrading of repeatability, let me say, of the experiment. It turns out that you can protect sort of part of the quantum state from decoherence, at least for some period of time, by taking whatever decoherence has happened to the whole state and kind of dumping it all into the other parts of the state. So the easiest way to think about this is actually kind of in a picture of a vector pointing somewhere on a sphere. So this is known as the block sphere picture.
The block sphere, yes.
Used a lot for qubits.
Yeah.
If you have something where, let's say, the vector is pointing somewhere at the equator of the sphere,
right,
and then you get random rotations about the vertical axis because of noise, and you average a bunch of these together, what it looks like is that the vector just sort of like decays towards the center of the sphere. It just gets shorter and shorter and shorter.
I see.
If it wasn't on the equator, if it was like tilted up from the equator, it would sort of decay towards the vertical axis, and you'd end up with just a shorter vertical vector.
I see.
What we can do basically is say, well, we know it's doing that. Let me rotate it down towards the equator at the exact same rate that it's shrinking back towards the vertical axis. And what this does is, instead of shrinking to the vertical axis, makes it shrink to the horizontal plane, to the equator plane. And so we're stabilizing the amount of the vector that's pointing along this equator plane. We call this a coherence stabilization protocol.
Okay.
And this was worked out by our theory collaborator, Daniel Lidar, who's another USC professor.
And another guest on the podcast.
Yes. He worked this out many years ago as just an example of, I think, how the block equations work for his class on open quantum systems. And his student was going to generalize this to sort of a much more general principle of stabilizing properties of quantum states, and wrote a theory paper on that, which is now published. And so Daniel came to me and said, hey, can you just demonstrate this? Like, we're going to do the generalization. Can we just show that it works experimentally? And so we said, yeah, cool, no problem. And it takes a little bit of work to get everything calibrated right and get all your systems set up right, but it was relatively straightforward. And we were trying to demonstrate the result. And to make things simple, to make the data look nice, we were trying to show it in a way that there was no sort of constant rotation about the z-axis, about the vertical axis, that the vector really just stayed pointing in one direction in the horizontal plane. And we kept finding it was rotating. We kept finding it was moving around in that plane. We couldn't calibrate it right. And we said, there's no way that we're doing this that wrong. Like, why do we keep missing? We know how to do this. And we thought, well, hey, it's behaving differently because we're doing this control. Does that make it more sensitive? And so we went and did some math, and this is my point of pride, that I actually went and did the paper and pencil theory on this, which is something that I'm normally terrible at. I'm just this side of being a plumber. I'm the one who does the cooling water and the pneumatic stuff, and I'm not the one who.
I had to say though, Eli, all the best experimentalists have that kind of humility of like, I'm just an electrician or I'm just a plumber. I think it kind of distinguishes you as probably being a really good experimental physicist, actually.
I hope so, yeah. So anyway, went and did the theory and found that, yes, indeed, it does basically give you more sensitivity to anything that would cause the vector to rotate. And so then we're like, okay, if you're more sensitive to something, that can be bad if you're trying to calibrate, but it also can be good if you're trying to detect.
Right.
And so that's where this application to quantum sensing comes in. And so it's useful then to back up and say, okay, like, what is the problem that we're actually trying to solve here? Like, what is the thing we're trying to detect, and how is it usually done?
Right.
So this problem is basically trying to figure out exactly how far apart in energy two quantum states are. And what happens is, if you put two states in superposition, there will be a phase difference between the states. Basically, one of them in that superposition is going to get multiplied by a complex number with magnitude 1, which basically has a phase in it. Equivalently, you could just say, like, it's this vector and it's rotating around the vertical axis. It's the same thing. And the rate that phase grows, or the rate that the vector rotates, is determined by the energy splitting between the two states. This is known as the Larmor frequency. It is very well studied in, for instance, nuclear magnetic resonance, which is used for MRI.
Interesting.
And it's essentially tells you, how far apart in energy these two states are.
Right.
Now, that's actually a really useful quantity to know, because it turns out there's lots of things that you might want to detect that you can sort of map to that. For instance, if you want to detect a magnetic field, you put two states that are sensitive to magnetic field, a system that has two states that are sensitive to magnetic field, and the energy splitting will change depending on the field.
Right.
And so you measure the splitting, you measure the field. That's also used for like temperature. It's used for how much deformation you find in a crystal lattice. There's all sorts of things you can detect this way. It's also really necessary for quantum computing to know what this transition is, so you can calibrate all your operations correctly. Yeah.
In reading the paper, that I got that sense that there was sort of direct sensing applications, as you said, magnetic sensing or those types of things, but also potentially benefits to a quantum, like if it was an embedded part of a quantum computer, it might actually improve things like calibration and coherence times, just intrinsic to the system itself, right?
Yeah, basically, you can use this to calibrate the frequency of your qubit, the difference in energy of these transitions, a little bit more accurately than you otherwise would in a shorter amount of time.
Interesting.
And so basically, you don't have to spend as much time calibrating your operations, which is good, because it turns out that all these things kind of drift around and you have to keep recalibrating them all the time. And that's downtime. And these things aren't cheap, so it would be nice to have them up and running as much as possible.
And in that setting, in that sort of aid to calibration, would that be additional sort of components within the additional superconducting circuits within the like non-functioning qubits, or would that just be a way that you're interacting with the qubits that do the computation?
It's just a way you're interacting. It looks very, very similar to the standard way we calibrate them, but it includes a little bit of special sauce that makes it more sensitive.
That's really cool.
So maybe it'll help to go through what the sort of typical way this is done.
Please.
And this is something that was invented in 1950, and I would say has been the gold standard ever since. It's called a Ramsey measurement.
Right. The paper makes mention to you beating the Ramsey
that was
threshold.
our claim to fame. So in a Ramsey measurement, what you do is you take a quantum system with two states. You take a qubit, and you put it in a superposition where it's sort of equal amounts of both states. So again, in this vector picture, it's like the vector is pointing somewhere in the equator. Then you let it just evolve freely. And it will rotate around the vertical axis. It will pick up this phase at a rate that's determined by this energy splitting. So you just let it go for some period of time. And then you do a rotation so that it goes back to the vertical axis, or tries to go back to the vertical axis. And you measure it, and your measurement basically tells you, on average, where on the vertical axis it ends up.
Right.
And this basically just tells you sort of where in the horizontal plane it was.
Okay.
So, and
that drift then gives you an indication of what the energy difference is between the two states.
Exactly. Basically, your measurement signal will oscillate depending on how long you let this thing rotate for. And that oscillation basically tells you the difference between that transition frequency and some reference frequency that you've set.
Okay.
And you know what the reference is, so then you know what the transition is.
Right.
The problem comes if you get really, really close to the right answer. It's going to look like it's rotating really, really slowly. And then it's also going to be, decohering at the same time. So it actually doesn't rotate very far before it just completely shrinks away. And all your signal goes away. Now, it turns out that basically what you're looking for is just that little bit of rotation, which just looks like a little bit of growth in the vector perpendicular to where it started out. And if you can maintain sort of the original part of the vector for longer, then you'll get more of that growth. And so the Ramsey measurement, does this in a way that you sort of maximize how fast your signal is going to grow right at the beginning. Our protocol sort of takes a tortoise and the hare kind of approach, where we start it out growing more slowly, but keep it going for longer. And the way we do that is, again, this coherence stabilization. We start it somewhere up from the horizontal plane. We start it like tilted, maybe 45 degrees or so from the vertical axis. And then we stabilize the part of it that's pointing in the horizontal plane.
Okay.
And we do that for as long as we can until we sort of just run out of juice, basically.
Right.
And
quantum juice.
Yeah. And then the signal that we were looking for, the amount of this rotation of the vector, is bigger. And it can actually be bigger by almost a factor of 2. Now, it does happen a little bit more slowly. So if you don't just need the signal, but you need signal fast, then it's not quite as good. It's maybe only a 20% improvement or so.
Okay.
But it's still a significant improvement.
Okay.
And so this is really the key, is that by stabilizing part of the quantum state, we allow ourselves to be more sensitive to small changes in that state.
Right. Yeah, that makes intuitive sense. And so, that's, as you said, there's sort of the flip side. There's the increased sensitivity in sensing, but on the other side of it, would it correlate to more accurate calibration, faster calibration, longer coherence time, or all the above?
So I would say on the calibration side, it's some combination of faster and more accurate.
That's great.
Basically, if you spend more time doing it, if you just average more and more times, you'll get more accuracy.
Right.
But there's some amount of accuracy that you want.
Yeah. No, it's nice having that kind of ability to trade off, right? It's sort of dial in the increase in accuracy that you need to get the most efficient kind of result you need.
Yeah. So this will get you either the same accuracy as a Ramsey protocol, but in less time, or it'll get you better accuracy in the same amount of time.
Right. Right.
And coherence, I would say, is not really the thing here, because this really only works when you know where the quantum state is the whole time, or at least you know where it started. And kind of the point of quantum computing is that it's, in an actual good quantum algorithm, we won't know that.
Right.
That's the whole reason we're doing it.
Yeah.
So this is more for calibration experiments.
Yeah. Got it. So which is obviously, even if you're going to run an algorithm where you're not going to know, like a Shor's or whatever, the calibration is a necessary step to get the system into a state where you can hopefully successfully run that algorithm. So it's a crucial part of the bring up process for a quantum computer. So, and is this the superconducting device that you're using, the qubit you're using, would this just be sort of a transmon, or is it what flavor of superconducting qubit would it be?
Yeah, this was a transmon qubit, which in terms of the math behind it looks exactly like a playground swing. The potential energy is exactly the same as what's called a physical pendulum, which is what a swing is. And I really, really like that, because that's maybe the first physics problem that I can remember wondering about was being a kid and swinging on a swing, and you can get going on a swing from a dead stop without ever touching the ground. You rock back and forth well enough and you can do it. And I remember thinking as a kid, how does that work? How can you possibly do that? The rope on the swing can only pull you up, or only pull you towards the pivot point. And it really took until grad school that I learned the answer to that. It's called parametric pumping.
Right.
And that's all classical. But if you do a quantum mechanical version of this, it looks like a thing that you can use as a qubit, and we call that thing a transmon.
That's really cool. That's a great analogy. Thank you. I'm always on the lookout for good analogies to try to bring, sort of our intuition to bear in these very, very exotic devices. But I hadn't thought about a playground swing before.
It's a quantum playground swing.
Yeah. Last episode, I was talking with Mohammed Mir-Hosseini from Caltech. And he was talking about his nanoscale tuning forks that he's making in superconducting devices. So
he's got the really exotic stuff where he actually does have things that are physically moving. I just have electrical currents that are going back and forth that look like things that are moving.
Yeah, exactly, exactly. And so you mentioned the protocol is applicable, obviously, it'd be applicable to other types of superconducting devices, cat qubits or dual rail or other more exotic sort of superconducting qubits. Do you think, would you expect the increases in sensitivity to be similar, or like how would you expect the protocol to play out in these other types of superconducting devices?
So I would say for most superconducting devices, it will be similarly effective. Maybe a little bit different in the sort of like exact amount of benefit that you get out of it. So it turns out basically one of the secrets of this protocol working well is that there's really two types of decoherence that we typically get in these devices. One is these sort of random rotations about the vertical axis that I talked about. We call that dephasing, because it sort of scrambles the phase of a superposition. And the other is relaxation, where basically it goes to a thermal state. For our system, that's a very, very cold thing. So the thermal state's pretty much the ground state. And that's actually really useful because you know where it's going.
Right.
So you sort of like know that if I leave it long enough, it's going to end up in this state, and that's actually coherence that's gained.
And that would be the equivalent of a bit flip, right? Going to the ground state.
Importantly, it's not like a symmetric bit flip. It's more likely to go to 0 than it is to 1.
Right.
And so we can use that to basically say, well, I know there's some reasonable probability that the state has gone there. Let me rotate that back to where I want it to be.
Right.
If your system has a very high temperature, what that means is basically the temperature is not small compared to that energy splitting. Temperature is sort of an average energy. Then the protocol doesn't work as well. Although it actually depends on some details of how you were setting up the state in the first place. So for some systems it will, for some systems it won't. It probably wouldn't work quite as well for a fluxonium qubit, but it would work pretty well, I think, for most cat qubits and most dual rail. The other thing is that the more your decoherence is dominated by this relaxation process, and the less it's dominated by these random rotations, dephasing, the better the protocol works. Because again, it's decohered, but you know where it went.
Right.
And that's useful. And I would say most superconducting qubits have a similar kind of amount of relaxation. That's the issue. Other technologies may have a different amount. So, for instance, trapped ions, I think in general just don't have relaxation. They really don't need to worry about it. And so in there, the protocol is not as effective. It's still better than Ramsey. It's guaranteed to be better than Ramsey, but maybe it's only 9% better than Ramsey.
Right. And in terms of when you think about next steps along this line of work, are you thinking exploring potentially impact on sensing experiments, on computing, more of a computing setting, or what would your next sort of set of challenges be?
So my lab mostly works on computing. And in particular, we've been doing a good amount of work on calibration and characterization. So we'll definitely push on that. We'll definitely use this to do better calibration of our qubit operations. I think it could be really exciting for sensing. The protocol will work. Superconducting qubits aren't a great sensing technology for the same reason that they are a great computing technology, which is that they're really well isolated from the environment. So, we did a lot of work.
It's hard to bring a superconducting qubit in close to something that you want to sense, right?
And I mean, it's almost sort of by definition that something that's good for sensing will be bad for computing and vice versa. Because the whole point of the sensing thing is you want it to be affected by some environmental variable.
That's true.
And for computing, you want it as isolated as possible from the environment.
Yeah, that's true. Does the protocol have a name?
We call it coherence stabilized sensing. And I don't know, it could probably use a snappier title.
Something. I mean, Levenson-Falk protocol sounds like
we would call it the Hecht protocol after Melita Hecht, who was the student that led the work. She led the experimental work on this and really did a fantastic job with the measurements.
That's great. That's awesome. And your lab? Are you sort of at a stage where you're shifting, like pivoting to something, some new topic, or are you going to sort of double down on this protocol?
So my lab works in a bunch of things. The only real common thread is that they're all involving superconducting circuits. And so we will probably continue this work in some form or another, but at the moment, it's not our biggest point of emphasis. We are definitely putting a lot of emphasis on gate calibration, on qubit operation calibration. But we're currently focusing on other parts of that problem. In particular, how if you're doing an operation on multiple qubits, what we call a 2-qubit gate, say, or a 3-qubit gate, or multi-qubit gate, basically getting one qubit state to change in a way that it's conditional on the other qubit states. You need to calibrate that. And you need to know how well it's working. And if it's not working correctly, in what way is it not working correctly?
Right.
And that is not at all a trivial problem. That is a hard thing to do. And the sort of like most complete version of doing that, if I want to know how a single 2-qubit gate works, I need to do 256 measurements.
Wow.
Which is a lot. And each of them needs to be averaged, and each of them maybe needs to be swept over how many times I'm doing the gate, and it's a mess. Okay, you can make some simplifying assumptions and maybe get down to like 64 or 100 or so. We're trying to get it down to like 9.
Wow.
And we think we've got a way to do it.
Wow.
Which I can't talk too much about because it's work in progress. But basically, we're trying to generalize a version of a protocol that we figured out for single qubit gates when you're just changing a qubit state, not conditional on anything else.
Right.
This is also work with Daniel Lidar's group. This is something we call deterministic benchmarking. Because there's a very well studied and widely used protocol called randomized benchmarking, which sort of tells you how good your operation is when very random things are happening.
Right, for arbitrary operations.
It turns out that's often an overestimate. It's often telling you that it's better than it really is. Because it turns out that if you just have the thing miscalibrated, not kind of like noisy, but just doing the wrong thing over and over, and you repeat it many times, which you often have to do in an algorithm, then those errors build up really fast. And you need to be able to tell the difference between that versus a random error that doesn't build up as fast.
Right. That makes total sense. That's really interesting. Well, I won't ask you more about those details since they're a work in progress, but I will definitely have you back on to describe that work. That sounds really fascinating. So thank you so much for your time, Eli. This has been really, really interesting.
Yeah, happy to help.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.